Imagine an investment strategy that costs less than $0.
Right.
Like an upgrade where you are literally paid to participate while simultaneously solving one of the most existential threats to modern civilization.
It sounds like a late-night infomercial scam, honestly.
It really does. But in 2012, one of the world's largest financial institutions realized this negative cost asset was the only thing standing between the global economy and a $38 trillion crisis.
Exactly.
So, welcome to the Deep Dive. I'm your host, and today is May 9, 2026. We are opening up a really remarkable time capsule today from Bank of America Merrill Lynch.
Yeah, it's a comprehensive report published 14 years ago, and it's titled Less is More Global Energy Efficiency.
Okay, let's unpack this.
Yeah.
Because opening this document today, it reveals a blueprint that just perfectly anticipated the macroeconomic landscape we are navigating right now.
It really did. The fundamental argument they constructed was that, in a resource-constrained world, the ultimate growth engine for the global economy wasn't discovering how to produce more energy.
Right.
It was doing less, engineering systems to run on a fraction of the power.
They identified energy efficiency not as some environmental charity case, right? But as the fastest, cheapest, and most ruthless economic response to an impending supply bottleneck.
Which is why, if you are listening to this right now,
Right.
and you're trying to parse the massive structural shifts in how we consume power, or if you're looking for long-term investment themes, this report is basically the foundational architecture.
Yeah, it explains the invisible why behind the design of your home, your car, the data centers, running the apps on your phone. But to really grasp why this less is more approach became the dominant strategy, we have to look at the terrifying baseline data they were modeling for the year 2035.
Oh, the baseline was grim.
It was. They projected a 33% increase in primary global energy demand. And just to clarify for everyone, primary energy demand means the raw, unconverted energy. So like the coal before it's burned, the crude oil before it's refined.
Right. And the geographical distribution of that demand is what made the math so incredibly daunting. 90% of that projected growth was coming from emerging markets.
Wow. 90%.
Yeah. China alone was expected to account for 30% of it.
That's huge.
Because when you analyze the mechanics of developing economies, an industrializing nation experiences this massive spike in energy intensity, pouring concrete, smelting steel, constructing heavy infrastructure. The thermodynamic requirements are just immense.
So the report modeled the sheer financial weight of this trajectory, and they calculated that meeting this soaring demand would require $38 trillion in global energy infrastructure investments by 2035.
Which breaks down to about $1.5 trillion of capital expenditure every single year, just to keep the lights on and the factories running.
$1.5 trillion every year. And the alternative, if the global market failed to build out that infrastructure in time, was devastating.
Absolutely. The report modeled scenarios where demand rationing could trigger oil price shocks pushing $200 a barrel.
Which is a pure mathematical limit. The global economy historically triggers massive recessions whenever energy costs exceed roughly 9% of global GDP.
Right. The system simply breaks under that financial friction.
So trying to solve this impending crisis purely by building more solar panels or drilling more oil, it's like trying to fill a bathtub while the drain is wide open.
That's a great way to put it.
You can blast the faucet on full volume, but the water still disappears. You have to plug the drain first.
And building our way out of that problem purely on the supply side just wasn't feasible. Attempting to substitute old power with new power-swapping coal plants for vast solar arrays or wind farms, it requires decades of permitting, immense capital, entirely new transmission infrastructure.
It's necessary, but it's really slow.
Exactly.
Yeah.
Efficiency, on the other hand, bypasses the infrastructure bottleneck entirely because it actually pays you.
Right.
The report establishes this macroeconomic rule of thumb. Every single dollar spent on energy efficiency saves $2 to $4 in lifetime energy costs.
Which fundamentally deletes the need to build the next expensive power plant.
Precisely.
And looking at the 2012 data, the proof that plugging the drain worked was already heavily documented. I mean, the refrigerator statistic from the text just blew my mind.
Oh, the fridge stat is wild.
Yeah. An average fridge in 1973 used over 2,000 kilowatt hours a year. Today, or, well, by 2012, under 700.
And the function of the appliance remains completely identical, but the underlying mechanism is optimized. which leads us to look at where the most significant structural energy traps were located.
Right. If plugging the drain is the goal, where are the biggest leaks?
Well, the largest vulnerability and simultaneously the lowest hanging fruit was the built environment. Buildings account for about 40% of global energy use.
And 30% of global CO2 emissions?
Yeah. And inside those structures, the triad of heating, cooling, and lighting accounts for up to 60% of the total power drawn.
So we were systematically paying utilities to pump thermal energy into poorly insulated boxes, only to watch it literally bleed through the walls.
Exactly.
Yeah.
But what's fascinating here is how they tackle the economics of fixing it, using this concept of the CO2 abatement curve. They place building efficiency in the net negative portion of the curve.
Okay, wait, I have to push back here slightly for the listener because I struggle with this financial logic. Wait, so you're telling me it literally costs less than zero to fix this over time?
Mathematically, yes, it confirms it. The lifetime energy savings of better windows, insulation, smart HVAC systems, they completely outweigh the upfront costs.
But human beings and, corporate boards rarely make decisions on a 20-year horizon. They care about this quarter's capital expenditure. The upfront cost is very real.
You're totally right. And what's fascinating here is how the report addresses that exact friction. You are dealing with split incentives.
Right.
Often the landlord pays for the building upgrades, but the tenant reaps the reward of lower utility bills. So
Right.
why would the landlord care? But strictly mathematically, when you discount for the time value of money, meaning even when you account for the fact that a dollar spent today is worth more than a dollar saved 10 years from now, the lifetime energy savings utterly eclipse the initial capital outlay.
The abatement cost is mathematically negative.
Yeah. So policy frameworks and new financing models, like energy service companies that absorb the upfront cost in exchange for a cut of the savings, were designed specifically to bridge that psychological gap.
Which brings us to lighting, which is the perfect microcosm of that transition. In 2012, lighting consumed 19% of all global electricity.
Almost a fifth of our power.
Just go into illuminating spaces.
Yeah.
Largely because the dominant technology was still the incandescent bulb. And when you look at the physics of a tungsten filament, it is a tragedy of thermodynamics.
It really is. An incandescent bulb is essentially a tiny space heater that just happens to emit a little bit of visible light as a byproduct.
Right. 90% of the electricity it draws is instantly lost as heat.
And the shift to light-emitting diodes, or LEDs, altered the global power load fundamentally. An LED relies on semiconductor technology, passing electrons through a microchip to generate photons without that massive thermal waste.
And the report projected that intelligent lighting management and widespread LED adoption could slash global electricity consumption for lighting by up to 2/3.
Up to 2/3. Viewing the grid demand curves today, that single technological pivot successfully decommissioned the need for dozens of major power plants globally.
Oh, wow. But, optimizing a static building is one thing. The report then moves from the visible structures we live in to the hidden industrial backbone that manufactures our world.
This is where the scale gets massive.
Here's where it gets really interesting, yeah. The thermodynamics of heavy industry. The report calculated that across the industrial value chain, from the gathering of raw energy to its eventual consumption in a factory, 80% of the energy is lost.
80%. It is a staggering amount of waste.
It's basically like ordering a 5-slice pizza, but the delivery guy drops 4 slices on the floor before it gets to your table.
That is exactly what it is. Industrial inefficiency is like boiling an entire gallon of water just to make one tiny cup of tea and then leaving the stove on high after you sit down to drink it.
The energy isn't just misplaced, right? It is actively dissipated into the atmosphere as useless heat and mechanical friction.
Right. Industry routinely accounts for a third of global energy consumption. And in 2012, that system was riddled with legacy equipment operating without nuance. You had massive industrial motors running at 100% capacity continuously, regardless of the actual immediate workload.
Right. Just always on.
Exactly. But a technology highlighted in the report as an enabler is the variable speed drive. To use an automotive comparison, running an old industrial motor is like driving a car with your foot permanently flooring the gas pedal and controlling your speed entirely by riding the brake.
That sounds exhausting and expensive.
Very. Variable speed drives act as an intelligent transmission. They dynamically adjust the electrical frequency supplied to the motor to perfectly match the required torque.
So simply implementing existing 2012 best practices, like variable speed drives and waste heat recovery systems, offered a pathway to improve overall industrial efficiency by up to 26%.
And that optimization extends from heavy manufacturing straight into the newer digital heavyweights, the information technology sector.
Oh, right, because the report captured the very early days of the big data explosion.
Yeah, between 2006 and 2011, global digital output grew by a factor of 10, and they projected another 29-fold increase by 2020.
The footprint of our digital lives is just physically massive. We treat the internet as if it's weightless, a cloud of data floating in the ether. But the global IT sector's carbon footprint back then was about 2% of the world's total,
Which is huge.
putting it on par with the entire global aviation sector. Sending emails, rendering graphics, streaming standard definition video, it required the same energy output as every airplane in the sky.
Because the physical infrastructure of data requires continuous baseload power, not just to run the processors, but to prevent the hardware from literally melting. The cooling demands are extraordinary.
Right. So what was the efficiency solution there?
The business case detailed in the report was the migration away from local on-premise servers to hyperscale cloud infrastructure. The efficiency gains ranged from 30 to 90%.
30 to 90%. Wait, I want to dig into how that utilization rate actually works because a lot of companies in 2012 were terrified to give up their physical server closets.
Yeah, they wanted the hardware in their own building. But an old corporate server sitting in an office closet might only process requests for a few hours a day. It sits idle, running at perhaps 10% capacity, but it still draws near full power and demands constant room air conditioning.
Right.
Cloud computing relies on virtualization. Hypervisors allow one physical machine to act as dozens of virtual servers, so you aggregate thousands of different clients running the physical hardware at 80 or 90% utilization.
And you pair that with hyperscale facilities located in colder climates utilizing free ambient air cooling.
Exactly. And the energy consumed per megabyte processed just drops precipitously.
Okay, so we've optimized the factories and the servers. Now, how do we move physical goods, people, and the electricity itself? Because optimizing a stationary building or a stationary data center is relatively straightforward. But the moment you have to take that energy storage and hurl it down a highway at 70 miles an hour, the physics completely change.
The transport problem is arguably the toughest.
Transport accounted for 23% of global emissions and consumed over half of the world's liquid fuels. And the most alarming variable in their model was the passenger car fleet, which was set to double to nearly 1.7 billion vehicles by 2035.
Right. But the authors of the report took a very pragmatic, highly analytical stance on the automotive sector. It was about evolution, not revolution.
Meaning they weren't banking everything on electric vehicles immediately.
Exactly. They recognized that while EVs were the ultimate endpoint, the immediate material reductions in energy consumption would come from an evolution of the internal combustion engine, along with hybrids, and a shift toward rail and bus travel.
Right.
They argued that environmental regulation alone would not be the primary catalyst. The shift would be driven by consumers demanding better fuel economy because they were feeling intense pressure on their wallets at the gas pump.
So the initial investment enablers weren't just the EV startups. It was the supply chain making traditional cars burn less gas. Things like lighter cars, gasoline direct injection, turbocharging smaller engine blocks.
Replacing heavy steel components with advanced specialty polymers. Because every pound of weight you shave off a vehicle fundamentally alters the physics of its momentum, requiring less chemical energy to propel it forward.
But eventually, we do have to talk about the grid. The report introduces the concept of the electronet, what became known as the smart grid.
Yeah, if we connect this to the bigger picture, the transition from optimized internal combustion to full electrification requires a completely reimagined power grid. A smart grid serves as the central nervous system for a highly efficient, renewable, heavy world.
Right.
And the absolute holy grail of this architecture is grid-scale electricity storage.
Which addresses the core friction of renewable energy, which is intermittency. I mean, the sun sets, the wind dies down, but human demand for power is stubbornly persistent.
It's a severe mismatch between generation and consumption. A solar farm might produce a massive surplus of energy at noon, but peak demand hits the grid at 7 in the evening when millions of people return home, turn on appliances, and plug in devices.
So grid-scale storage allows utilities to bank those surplus electrons, chemically or mechanically, and then deploy them during peak hours.
Without that buffer, the mass electrification of the transport sector is impossible. A grid without dynamic storage cannot handle the localized load spikes of millions of high-capacity EV batteries plugging in simultaneously.
So what does this all mean for you, the listener? When you synthesize this 2012 roadmap, Investing in the less is more philosophy doesn't necessarily mean buying into the abstract concept of green energy. It means identifying the enablers.
That's right. The companies manufacturing the unglamorous, highly technical components that reduce systemic friction.
The smart meters, the advanced building insulation materials, the variable speed drives, lightweight auto parts.
And to summarize, the overarching message energy efficiency isn't just a nice environmental talking point. It is the most compelling economic imperative of our era.
Absolutely.
The International Energy Agency constructed a pathway known as the 450 scenario, designed to stabilize greenhouse gases and limit global temperature rise to around 2 degrees Celsius. In that deeply ambitious model, end-use energy efficiency is responsible for over 50% of the total required CO2 savings.
Over 50%. That's incredible.
It outpaces renewables, nuclear power, and carbon capture combined. Efficiency is the foundational heavy lifter of the modern economy.
It is the ultimate economic lever. But before we conclude this deep dive, I want to leave you with a final, unmentioned psychological puzzle to mull over. It's a concept built squarely on top of the source material we've covered, known in behavioral economics as the Jevons paradox, or the rebound effect.
Oh, this is where engineering collides violently with human nature.
Exactly.
The paradox is named after William Stanley Jevons, who observed in 1865 that introducing more efficient steam engines didn't actually reduce the consumption of coal. It accelerated it, because the efficiency made coal a more cost-effective tool for a wider variety of industries.
Right. We've spent this entire conversation talking about plugging the drain of the bathtub to save water, but the Jevons paradox poses a chilling question. If we engineer all these brilliant, sophisticated ways to make energy incredibly cheap and highly efficient, does human nature dictate that we will simply consume more of it?
You see the exact same behavioral threat in consumer energy today. Think about highway expansion. City planners add 3 lanes to a congested highway to improve the efficiency of traffic flow.
Right, but the wider highway induces new demand. People who used to take the train decide to drive because the road is newly clear. Within a year, the wider highway is completely gridlocked again.
Exactly.
So if your electric vehicle is incredibly cheap to charge and highly efficient, do you pocket the savings, or do you decide you can now afford to commute 50 miles further a day? If the energy required to cool a massive data center drops to near zero, do we rest on our laurels? Or do we invent entirely new, computationally hungry artificial intelligence models that devour the newly freed capacity?
It's a profound question.
If the bathtub train is finally plugged and the water is practically free, do we just go out and build a much bigger bathtub? Thank you for taking this deep dive into the forces shaping our energy future. Keep questioning the systems around you, and we'll catch you next time.